Okay, so concavity, whether it's concave up or concave down, the situation is that that is something that is determined. You can look on the graph here with me that's shown here and recognize that concave down, I don't know how you've learned it, but I kind of remember hearing the cave is facing up. So it's concave is up, and concave down is where the cave is facing down. So that's concave down. And concave up, concave down. And something else that's coming in just a second is where it changes from concave down to concave up, or the other way around. That is where a point of inflection occurs, okay? So I want to catch that while we got that going. But concave up is saying that if you notice it's concave up, that the graph, if you draw tangent lines, all the tangent lines are below F. F is above all of the tangent lines. It lies above each of its tangent lines, okay? And concave down, if the graph of F lies below all the tangent lines, okay? The tangent lines you draw to it, the graph is below it. And from this side, the graph is up, okay? That's how they define it. However you look at it, it's cool, but knowing concave up and concave down and distinguish it is going to be different. It's going to be important, okay? So let's go to the next situation. So notice this. This is the second derivative test. The second derivative, if it's greater than 0 on the interval, then it's concave up. And if the second derivative is less than 0, if it's negative, then it's concave down. All right? So I want to go back to, let's go back to the problem we just did and talk about, I'm gonna share a new screen and go to back to my iPad. Okay, and bring up again what we just did with this problem. Concave up and concave down, okay? So the easiest thing when you're going to go to take the second derivative, here's the first derivative right here, is you factored it. We've got this factorization down here. Taking the second derivative, don't go to that. Just go to the first derivative right here. If we've got f prime of x, I'm going to write it out just like it is. And then from there, we can take the second derivative. X, that is x, plus 12. Then now the second derivative we take of this. If you go to the factored form, it's cumbersome. Taking the derivative means you got to use the product rule, et cetera, da, da, da. But the most straightforward is just take the derivative of this. What do we get? 12x minus 18. Factor that. We got 6 is common, right? That gives us 2x minus 3. Isn't that special? That wasn't the easiest one to pick, but notice what's happening. If we pick a value on the interval to the left of our graph, if we pick a value to the left, like if we plug in the critical point, 1, into this function here, notice what we get. The second derivative at that critical point is 6 times 2 minus 3. We get 6 times minus 1. That's equal to negative 6. We get negative 6. Plug in 1 here, and you get negative 6, and it's concave down. This is negative, therefore it's concave down at 1. That interval, that portion of it is down. Look what if we plug in 2. 2 is at the bottom there. So if we plug in f double prime, plug in 2 into that, we get 6 times 4 minus 3, which is 1. We get 6. That's positive. That means it's concave up, okay? And what can be confusing, so that means it's concave up. What can be confusing about it, it's positive, it's concave up, therefore it's a local min. This is happening at the bottom because it's concave up. This is at the top, so it's a concave down, it's a local max, okay? So local max, if you're being asked to determine whether it's the local extrema, if it's concave up, you got a min because it's at the bottom. If it's concave down, you're at the top, therefore it's a local max, okay? That's happening there. So let me go back to the screen. Any questions on that? Okay, so let's go back to our test for concavity. We've got the second situation there. That was that. And I wanted to also then go to talk about an inflection point. That's coming next. Okay, so the point of inflection, some people call it a point of inflection, some people say inflection point. But notice this. Suppose f is a function that's differentiable on an open interval containing f. The concavity of f changes at some point, then that point is an inflection point, okay? So if the concavity changes at x equals c here in our picture, what we've got going here, then c, f of c, is the inflection point. And then as a follow-up to that, notice that a condition for an inflection point. Notice it's positive if it's concave up, it's negative if it's concave down, but in between that, if it's zero, then that's a possible point of inflection. But you can get zero sometimes and it not be a point of inflection. But look at that second thing again. I'm going to point that out again. Let's look at this. If f is a function, is differentiable in the open interval, if f of c is an inflection point, then either f prime of the double prime is zero or the second derivative doesn't exist. So both of those could happen, and I'll give you some examples of that really, really soon, okay? So this is an example that is talking about a fractional situation. Let's go back to the second derivative test, the way they've got it written out clearly here, all right? What we did was we plugged in the point of inflection. So the second derivative test is, if you take the second derivative and plug in the point of inflection, the x value, if it's greater than zero, then that means it's concave up and you've got a local, if it's greater than zero, well, they goofed. Then f of c, if it's greater than zero, then it's a local min. The typo, they goofed. We're gonna have to cancel this because if it's less than zero and it's negative, therefore it is concave, that means it's concave down, then it's gotta be a local max. They messed that, okay? They haven't fixed it. We talked about that last semester and they haven't fixed it. So that's an issue. So the idea is if it's concave up, then it's gotta be a local min. Typo here. If it's concave, if it's negative, if it's less than zero, that means it's concave down, then it's gotta be a local max. Typo. Okay, so if the second derivative does not exist at a critical number, then you can't use the second derivative test. Okay, and then also if the second derivative test exists, but equals zero there, if the second derivative gives you zero, notice both of these. It's positive or negative, that means it's concave up or concave down, it tells you something. If it's zero, then you don't know, okay? We'll do a couple of examples of that and go from there. I'm really sorry about that slideshow not being fixed yet. I feel bad about that. Let's go to one more example, a new share. I want to go to my iPad and do another situation here. Okay? So, so we'll use the first derivative test and the second derivative test real quickly on a function. All right? Let's look at this. So f of x. I ask you to use the first derivative test and second derivative test. X cubed minus 6x squared plus 9x. Sapling gets into some problems that aren't just polynomials, and they challenge you a little bit with your algebra. So make sure you can do those, but what I'm going to be handling on the quizzes and stuff is mainly going to be polynomials, okay? So let's use I'm going to use the first derivative test and see what the local extrema are. So first, what does it look like? Looks like this, local extrema, there and there. Let's see what happens with this problem, okay? So I've got to have a max and a min there. Let's first find the critical numbers. So first we're going to find the critical numbers and find out our intervals, a positive or negative, and also local max and local min type situations. So f prime of x equals 3x squared minus 12x plus 9. Yes, that equals, factor the 3 out now. X squared minus 4x plus 3. So what do I have? I've got 3 times factor. It's got to be 3 and 3. It's got to be 3 and 1. And 1. And they're positive. The 3 is positive here. So they both got to be negative then. So x minus 3, x minus 1. So we've got x minus 3 equals 0. And we've got x minus 1 equals 0. So this must be at 1 and at 3. Okay? So if you're asked, where's a local, use the first derivative test to tell if it's a local max or a local min. You should do the first derivative test. Okay? If you're asked where is it increasing and decreasing, you've got your endpoints here, and you can see what those values will be. Okay? If it's increasing or decreasing. But right now, let's do the first derivative test. And that means I need to check something to the left, in the middle, and to the right. To the left, I'm going to pick 0. You can pick any number over there you want to, but the closer to the number set you can, the better. But and easy numbers to work with will be ideal. An integer in between 1 and 3 is 2, and to the right of 3, the smallest one is 4. So I'll pick those 4 numbers and see what we get. Now, is the derivative positive or negative is what we're doing with the first derivative test. First derivative test. Okay, so what I'm doing is I'm going to plug in f of 0. I'm finding the slope. So I got to plug it into f prime of 0. F prime of 0 equals, I'm going to just plug in 0 minus 0 plus 9. I'm picking out this function, right? I'm just figuring out what the slope is. That gives me 9. That means it's positive. Positive, that means it's positive over on this side. It's obvious what the answer is going to be, but if I ask you to show your work, you need to do it. F prime of 2, I'm going to plug this one into this part. It's a little easier to work with. I get 3 times 2 minus 3 times 2 minus 1, which gives me 3 times minus 1 times 1, which is minus 3. So that's negative. So that means in between here and here is negative. So that tells me what I want it to. And then in between, and then the far right one, f of 4, f prime of 4, I'm taking the derivative again. I'm going to plug that into the factored form because that's a little easier too. So I've got 4 minus 3 and 4 minus 1. So I've got 3 times 1 times 3. This is 9, which gives me a positive. So this is positive. So when we go to 1, all right, we've got increasing and decreasing. Therefore, increasing on the left of 1, decreasing to the right. Therefore, x equals 1 is a local max. And at x equals 3, we went from decreasing to increasing, negative to positive. So at x equals 3 is a local min. That is using the first derivative test to determine that, okay? Second derivative test, real quickly. Let's do this. So this is the first derivative test. The second derivative test is I take the second derivative. So I've got the first derivative is equal to 3x squared minus 12x plus 9. What's the second derivative? I get 6x minus 12. We've seen that before, haven't we? That equals 6 times x minus 2. All right? Well, the second derivative test, plug in the critical values. And I'm going to plug in, and that's the second derivative. So if I take f double prime of 3 and f double prime at 1, I'll determine if it's a local max or a local min. plug in 3 into this function, I get 18 minus 12, which is 6, which is concave up. It's positive. That means it's got to be a local min, which agrees with what we were talking about up top. That's a local min. And then if I plug in 1, I should get a local max. I get, if I plug in 1, I get what? 3 minus 12 plus 9? No, second derivative. Second derivative is 6 minus 12, which is minus 6, which is negative, which means it's concave down, which means it's a local max. Okay, so if you're finding that information, plug it in and get that situation. That's the information you needed. So the answer would be 3. I have to, at x equals 3, I got to plug, if I wanted to know the y value, I got to plug it back into the original function. F of 3 is equal to 3 cubed minus 6, 3 squared plus 9 times 3 plus 30 equals 27 minus 6 times 9 is 54 plus 27 plus 30. Notice what happened here. 54 minus 54 is 0. That equals 30. So 3 is 30. So we got a local min at 330 is a local min. And local max is going to be at f equals 1, f of 1. We get 1 cubed minus 6 plus 9 plus 30, which gives me 10 minus 6 is 4. That's 34. And notice it is bigger. So we end up with 34. So the coordinate here is 134 would be considered the local max. Okay, that's the second derivative test, finding, and then we had to use the first derivative to determine whether it was increasing or decreasing, the second derivative to find out if it was concave up or down, and we went back to the original function to find out the value of the function so we could answer the question. Okay, questions on that? Okay, tell you what, that's as far as I want to go right now, and we'll do some more stuff tomorrow. And let me know if you've got questions. Get going on the practice problems, on sapling problems, I mean, and go from there.